Welcome, everyone. Dear colleagues, it's a great pleasure to welcome you to today's inaugural lecture by Maksym Yarema. As head of the Department of Information Technology and Electrical Engineering, I would like to welcome Maksym and all of his guests today to the inaugural lecture. And it's a really great pleasure to see you in person. Clearly, this is inaugural under unusual circumstances, but you have put everything in place. Lovely people at the entrance to make sure that we comply with all the regulations. So Maksym joined our faculty in January 2020, and he leads a research group at the Institute for Electronics, where he focuses on chemistry and materials design. He was born and raised in Ukraine, where he received both his bachelor and his master degrees in chemistry. And that was at, and I probably mispronounce it terribly, I apologize, Lviv National University. So he has since been moving westwards. In 2012, he obtained a PhD at Johannes Kepler University in Linz. And in the same year, he moved on to Switzerland, where he became a member of the ETH domain. So first, he was a postdoc at ENPA. Then he became an Oberassistent here at ETH. And now, as I mentioned, he is an assistant professor in our department. There are many wonderful things I could and should say about Maksym, but for lack of time, I will say just two things. Namely, first, he is an excellent teacher. He told me actually that his parents are teachers too, so I dare to say that teaching may be in his blood. Indeed, his teaching efforts have recently been recognized here at ETH by an Innovedum grant. And this, as you know, is a grant that is awarded to support innovative teaching approaches here at ETH. And second, of course, he's a brilliant researcher, and he's the recipient of several prestigious grants. And I'll just mention a Marie Curie grant from the EU as a postdoc, an SNF Ambizione grant, and most recently, and that's what's made you professor here, an ERC starting grant. His interests span various topics of chemistry, including material science and chemical engineering, but a particular focus is given to, and I'm not sure whether I pronounced that correctly, colloidal nanomaterials, which is also the topic of your lecture today. So Maksym, in closing, I would like to say we are absolutely delighted to have you in the department. Your expertise complements and completes the scope of our department, and you are a wonderful colleague. You're always willing to help and always willing to contribute. This is greatly appreciated. And now we're looking forward to your inaugural lecture. The stage is yours.
Thank you, Klaus, for this very, very warm introduction. Dear ladies and gentlemen, welcome to my inaugural lecture. So today I'm going to talk about these small spherical objects, but no worry, these are not coronavirus. This is the colloidal nanocrystals. So you see they are very beautiful, they are captivatingly complex, and they're also very, very small, the sizes in the nanoscale. I seem to like complex objects from the very beginning. So this is probably about the first such complex object I see in my life. As you see, this is a spinning toy which parents put on a crib to make kids asleep or awaken. And at that point, I probably thought, what is this weird creature spinning on top of me? And later, I got to know that these are actually animals. Then, at the age of 3, many more things are becoming possible in terms of like having a bit more complex toys. And this is something I got fun to work with, to play with as a kid. For example, many construction games of some of these puzzle toys I enjoyed a lot. Then there was a school. There I got to learn how to write, how to count, a little bit of music, some more trainings, and even more trainings, and at some point there was a lot of mathematics. But nothing was as complex as to commit life to. until this. Somewhere at the age of 13, I met this molecule and also another molecule and many more. I must say I had a very good chemistry teacher at school, and she runs a very small but real chemistry lab in our school. And this I got access to, and at that point I was really mesmerized. Are we actually consistent on all these small materials, on all these small spheres? And even more than that, I was thinking, hey, why do they order this way? Why some materials are ordering like tic-tacs, but the other materials are actually very well ordered? And what's the difference? And I had millions of questions. I did answer some of them, but not all, until now. But this seemed to be complex enough to devote your life, to commit. So I stick to chemistry for a while, since that age, and then somewhere at the age of 22, I entered the PhD, and this is where I met this object on investigation. I would like to thank you to Wolfgang Heiss, my Dr. Vater, who is in the audience, and who showed me this object of investigation. And at that point, I thought, wow, so this is colloidal nanocrystal. I thought, well, this is the best of both worlds. Why? Because it has an inorganic core, something that belongs to the inorganic non-living state, but it has also nice ordering here, but it also has a shell around this material which belongs to organic world. So I thought, okay, my skills to know both chemistries would be in use. So today for this lecture we are going to focus on the core of these colloidal nanocrystals, but organic shell around would deserve actual lecture of this kind. So here you see how the nanocrystals looks in reality, no sketch anymore. Each of this sphere here is a small colloidal nanoparticles. So we see that we are able to control them very well to get to the very good uniform size of these materials. And because they have a very uniform size, they also order in this beautiful hexagonal lattices. Here's a slide about the synthesis of nanoparticles. This is the slow motion video, and you see that the synthesis is an addition of one chemistry into the other chemistry, which initiates the rigorous mixing of materials, and at some point, very fast, all nanocrystals form and materials become dark. It's a fraction of seconds when it all happens, and this is a key success for the colloidal synthesis. All right, but in a nutshell, synthesis is actually very, very simple. I like to tell to my students that this is as simple as A plus B. So in order to make a material, like AB material here, we will mix A material from this funnel to the B material, for example, which is in the flask. But there's a twist. We need a secret ingredient for this synthesis, which is an organic molecule, if you remember, which is around the colloidal nanomaterial. And this organic molecule would slow the kinetics of the AB formation to the extent it slows it down because it pacifies the surface, to the extent that you get a control over the size and shape of colloidal nanomaterials. This is what happens in the flask. For example, if a component A would be an indium salt and the component B would be an antimony salt, as you mix them with a secret ingredient called surfactant, in this case alkylphosphine, and we are lucky with the choice of temperature, with the choice of time and concentration, then we will be able to obtain a nice-looking nanoparticles surrounded by the organic molecules. All right, so let's start with the lecture after we pass this intro, and increasing complexity. As you remember from the periodic table of elements, there are about 80 stable elements in the periodic table. Let's take, for example, indium. These are the small nanocrystals you've seen on one of the previous slides. So now if we would like to increase the complexity to the two-component materials, which we call binary, then there are about 3,000 unique combinations of different elements, so complexity already increased by a few orders of magnitude. Let's go even more complex. Let's choose 3 materials to mix together. Then there are about 80,000 of different systems we could work with, and I should say that each of this combination of material, for example, in this case, copper, indium, and selenium, can have more than one compound, so it's even more compounds to study. What about 4 components? It's already more than 1 million of unique combinations, so it's a really very open-end the field for the science. And so now guess which system I decided to study for my postdoc central project. The bottom one. So this will will bring me to the first chapter of this lecture. Copper, zinc, indium, selenide nanocrystals, mass in the cationic sublattice. Let's start with something simple. What you see on the slide is a thin blend type crystal structure. It's one of the most stable semiconductor material. You can think about that as the arrangement of tetrahedrons, and each tetrahedron here is having in the center selenium. The vertices of this tetrahedron that are shared between different selenium centers tetrahedrons are cations. So now the stoichiometry between cations and selenium in this case would be 1-to-1. And these materials are very stable semiconductors, like 3,5 materials, for example, gallium arsenide, or 2,6 materials like zinc sulfide would belong to this structure type. Let's increase complexity. If we would just take the cations and split them half to element 1 and half to element 3, for example, copper and indium, then we end up with another semiconductor materials called 136 semiconductors. For example, copper indium diselenide, which is very famous for the photovoltaic applications. We add another element, say zinc here, for the cationic sublattice. And this also creates some atoms to be missing due to charge phenomena. And now I may ask a good solid-state chemist like Wolfgang, is this going to be a good semiconductor? I see the criticism there because this is exactly the case. A good scientist would say, no, you are crazy. There are too many elements to mess up with. And all these elements, they can mix, and there are probably 20 or 30 or 40 different defect states in the band gap which would literally screw up the semiconductor. So with this counterintuitive motivation, we start that project. So the strategy for this project was like that. We decided to mix the elements and to tune the composition of these elements in the form of nanoparticles. To simplify it a little bit, we fix the size of these nanocrystals always to be about 3.3 nanometer in size. So we see from the TM image, they have a narrow size distribution, they are 3.3 nanometer, only composition is tuned. And so we decided, let's see if we find something interesting in terms of composition properties under quantum confinement. And that's what we found. So what you see on the slide are the measurements of photoluminescence efficiency, which is, in other words, how efficient is light coming out of the material. So we see this as a function of different compositions. Once again, all these red points here are the compositions which we achieve experimentally. They have the same size, but different composition. And we immediately see, if I plot it for you, for example, at the scale of copper content, we immediately see that there are two outliers. There are two good outliers because the properties of these two materials, the light they shine back to us, is superior in comparison to their very much neighbors. So we found some sort of optimal copper, zinc, indium, selenide compositions in terms of lighting applications. We were not the first one to find it, of course. So there is already this family of materials called order vacancy materials. For example, 1 to 5 to 6 stoichiometry of materials should have every fourth cation missing, which you see on this sketch. So there is an ordering of the vacancies in the green net. And this brings us to the best PL quantum confinement. There are more of this family of materials, and the ordering for them is not yet known, and now we add yet another one, which has 4 components with it. But our goal was not to find another one, was to explain why these peaks are happening and generally what is going on. So the first step was, let's assume that we have a random ordering for the cationic sublattice, for the copper, zinc, indium, and vacancies. So as you know from the previous slide, the zinc blend type structure can be presented as the array of the selenium tetrahedra, and there are 35 theoretically possible tetrahedron around this selenium. This seems fairly complex, but it's actually quite simple, because what we can learn from the combinatorics is that we actually can calculate the occurrence probability of each of these tetrahedron, and what is simple is that the percentage of the tetrahedron would be directly proportional to the mass fraction of the components that are there, plus a small combinatorial factor. And so what we learn from this assuming the random cationic sublattice, is that we can match some of the occurrence probabilities with the quantum field directly. So this shaded area here is a random cationic occupancy. It's a probability of a small structural unit which has copper and vacancy in its structure, copper vacancy couple, let's call it this way. And it can explain the background feature for the efficiency of luminescence, light coming out. What's even more intriguing is that some composition we can order. And with that we increase the probability of these copper vacancy couples. So in the nutshell, we explained that the occurrence probability of copper vacancy couples is proportional to the luminescence, so it can explain both composition and ordering trends. And this is what you see. This is the structure of this copper in orange and the vacancy in the semi-shaded red. So with that, we answer where the light is coming from. So the copper and vacancy couple is this working horse for this material. So the more you have of this, the more efficient your light is. And you can check it yourself here on the left slide, or the left side of the slide, you see the experimentally measured luminescence efficiency, and on the right side is the occurrence probability for the copper vacancy containing units. So they pretty much match to each other. Why it is relevant? It's relevant for lighting applications. So these are the colloidal vials of materials which we have. When we shine high energy light at them, they will shine back a very, very uniform light for us, very clean light. And of course, this most efficient light is coming from the ordered compounds. Okay, let's switch gears to the second chapter of this lecture. It's about intermetallic nanocrystals and about unique atomic arrangements of them. So when it comes to intermetallic nanocrystals, it is already quite difficult to combine 2 different metals. So what are the intermetallic compounds? It's a huge family of materials. It's about 20,000, it's more than 20,000 compounds, binary compounds, and every day, every week is a new getting found. So for example, there's about 1,000 of materials with a stoichiometry 1:1. As it comes to intermetallic nanocrystals, it's only a few percent which are reported so far, and everything is remained in this great unknown space. So we ask ourselves at the beginning of that project why this is the case, and the basic answer for that is just because metals are very dissimilar. So there is a different ability for different metals to reduce, and in the flask, as soon as one metal is going to the metallic state, it pushes away the second one, so-called redox reactions, for example, galvanic exchange, and so on and so forth, different side reactions, which would prevent us to do a homogeneous intermetallic nanocrystals. So we set ourselves a goal to be able to do intermetallic nanocrystals, even combining very dissimilar metals, like gold, very easy to reduce, and gallium, very difficult to reduce. And this is how we went about it. So we use the so-called amalgamation synthesis. We use the amalgamation reaction. Amalgamation is the alloying between 2 metals, one of which is in the liquid form. So having one liquid metal is a key for the synthesis, because the diffusivity of the liquid is much faster than the diffusivity of the solid, and so the material that is liquid creeps through the solid very fast and very homogeneous. So our synthesis is simple. It has 3 stages. So first stage would be to synthesize monometallic seed nanocrystals, and here we are very thankful to all people who were before us. They made so many monometallic seeds already, like palladium, gold, copper, nickel, and many more. So our task was to supply the low melting metal to the surface. And this is how we did it. So we choose alkylamides and silyllamides of different metals because we know that at high temperature these compounds would decompose, leaving behind metal and easy leaving byproducts. We were successful with this dispatch of liquid metal. So as you see here on the compositional map, there are these yellow regions at the surface of nanoparticle, which are the gallium islands. And so as soon as we have a gallium there, then we trigger the diffusion of the gallium inside the nanoparticle, and the third stage is simple. Only we need to do is wait. Fortunately, we don't need to wait very long because diffusivity of liquid is much faster than the diffusivity of the solid. Here you see an example of what we can obtain using amalgamation synthesis. These are nickel-gallium nanoparticles. Again, as you see, they have a very uniform size, and from the composition map, you can see that the composition of each nanoparticle is the same. In this case, it's about 1-to-1 ratio. Okay, talking about universality of our method, we can decompose different amides on the chosen seed, and other way around, we can choose different seed and decompose the amide on its surface. So let's take, for example, palladium seeds and decompose gallium, indium, and zinc salt on its surface, and this will convert our palladium seeds to bimetallic palladium gallium, palladium indium, and palladium zinc materials. So you see from the X-rays that the materials are phase pure. Each nanoparticle has a very good crystallinity. We can achieve composition control and size control, as well as composition and size uniformity. The application for that, the question again, why it is relevant. One immediate application for that would be plasmonic materials. To remind you that plasmonic is a movement, collective movement of electron cloud in response to incoming electric field or light. And so you see here schematics, and this will trigger certain resonance at certain wavelengths. A very good material for plasmonics, York can prove, it's gold nanocrystals. And copper nanocrystals, for example, is not considered to be good. It's actually a good, has plasmonic resonance, but copper nanoparticles are too easy to oxidize, but not our copper. Our copper is oxide protected, so we decided to do this. We choose amalgamation synthesis to make copper nanoparticles which are protected with a small oxide shell. So you see here a compositional map. Each of this nanoparticle has a small crust of gallium oxide. How we made it? We just add a very little of the gallium salt, so we collect gallium only on the surface and oxidize it at ambient. And so now you see this flask here that after 1 day of storage, the copper only would get oxidized, and this would give us the blue-looking solution. The complete oxidation of copper nanoparticles to copper 2+. But the gallium oxide protected copper sustained the plasmonic properties at the same conditions. It's, of course, more to come for the intermetallic nanocrystals. We unlocked hundreds and hundreds of different bimetallic compositions with this method, and we always ask ourselves about this link of structure and functionality. And functionality of applications for intermetallics are vast. It could be a thermoelectrics, energy storage. It could be also many other applications like catalysis, where unique atomic arrangements of intermetallic nanocrystals are important. So we always ask ourselves this question. For example, copper-gallium bimetallic has a sheet of copper in between these gallium slabs. Is it actually good for catalysis? Or the other compound, gold-gallium, has a very symmetric cubic fluoride type lattice. Is that good for plasmonics? So these are some questions we are going to answer in the future. Now, this is my last chapter for today. It's about amorphous nanoparticles, and the story there is these are the nanoparticles which actually have no atomic order in the initial state. So the story is like that. We mix germanium iodide in the flask with the tellurium from the funnel, and then these are the nanoparticles which we obtain. They look normal, they look like a regular shape, and they look okay, small. But when we look at them closer, and even more closer, we were like, all right, there is no atomic order for these materials. So we don't really see any atomic arrangement if you look close up at them. Otherwise, nanoparticles are like normal. We can tune the size of the germanium telluride nanoparticles. The composition of them contains germanium and tellurium, but they have amorphous structure, which is shown here by X-ray diffraction having no peaks. So then we decided with Olesya, what shall we do? Shall we basically hit this material to see what's going to happen? And then we did that. We measured X-ray diffraction at different temperatures, and at some point we start to see the peaks appearing. And so these peaks will tell us that we become to have ordered material. So our disordered material at low temperature become ordered at high temperature. So you basically see a close-up of one single peak here, and then from nothing arises something. And we also have a supplementary TM measurement showing that material has no atomic arrangement up to 200 about, and already at 300 it already has some atomic, very clear atomic arrangement. Luckily, this property is size dependent, and then we can find the size dependency of this crystallization phase transition, and then we can find a very good, very promising application for this phenomenon. The application is called non-volatile phase change memory. This is a new storage class memory that is already better than silicon transistors. So it's on the market, and basically the working principle is very simple. This is a structure conversion of the same material from the amorphous to the crystalline through the crystallization and melting phase transitions, which brings us to the logical 0 state, highly resistant state, and logical 1 state, low resistance state. So the nanoparticles with the size-dependent crystallization and also size-dependent melting are given an additional parameter to tune. So one may say this is a game changers for the phase change memory applications, because now if we are entering a sub-10 nanometer size for memory dimensions, then we should care about the size dependence and choose the material wisely. Some more benefits from colloidal nanoparticles is a ultra small sizes of memory devices, like a single nanoparticle could be the one, or a very simple and inexpensive solution-based fabrication. So one question we are working on currently is what is the structure of amorphous germanium telluride nanoparticles? So you basically see the crystal structure one can imagine very well. So these are the arrangements of atoms. Each of this black dot here is a column of atoms. But for the amorphous structure, it's difficult to classify. It's not possible to see here from this image anything, but is that actually possible to somehow imagine the amorphous structure, to understand what is amorphous? All right, we need a good method for that. So we stumble on one method called X-ray absorption spectroscopy. So essentially what we are measuring is a absorbance of incoming X-ray beams as we tune the energy of these X-rays. This is type of data that we usually receive. It has the edge, which tells us which element we are looking at. In this case, we are looking at germanium edge. And then after the edge, we have this post-edge irregularities, which is constructive or non-constructive interference of X-rays as they scatter out of different atoms. We are interested in this post-edge region because this region is a function of which atoms we have around, how many atoms we have around, and what is the distance between our absorbing atom and all the other atoms around. So what we usually do, we do a Fourier transform of this plot And by doing that, we kind of look from the point of view of this single atom of interest, in this case, germanium. And we observe this, so to say, radial distribution function has a forest of peaks, and each peak position would be proportional to the distance between our germanium atom and other atoms around here, like this green or golden. And the intensity of these peaks would tell us something about how many of these atoms we have around our germanium. So we can do that as a function of temperature. Of course, we can do this radial distribution, and here you see this heat map while we heat in our germanium telluride nanoparticles. Clearly, something is happening at about 300 degrees, because you see that these peaks actually change to the other one. As I said, we can estimate, we can calculate actually the amount of neighbors, coordination number, and also the distance to these different atoms, average bond distance. And we do it for different temperatures, and these are the plots I would like to explain a little bit. So what do we see? We see that this continuity, which suggests us, it points us to that there is this crystallization happening at about 300 degrees C for the sample. So of course, while crystallizing, the atomic structure rearranges, and then the bonds that we have, they change their lengths quite abruptly in this case, and also structure is getting linked differently between crystalline and amorphous. Let's focus a little bit on the amorphous side. This is this region. So it looks like, two conclusions from that plot. It looks like that amorphous structure is not really very linked. So it has relatively low coordination number for the nearest tellurium bond, which one can intuitively guess because it's amorphous. And what is another interesting feature is that amorphous structure has a lot of germanium bonds. So which means some of the atoms in germanium telluride structure would switch their position, and this will give us a germanium bond. So what's convenient in this case is that the amount of this germanium and germanium tellurium bonds is about the same. So we looked in the literature and did a following thought experiment. So we do it in 2 dimensions first. So for crystalline, again, one expects to have octahedrons. So this would be this shape. And then you can make a space regularly just using this octahedron. Now what about amorphous? You remember that we have 2 different units, germanium and germanium tellurium. This would correspond to so-called tetrahedron and bridge tellurium units. And they should be about 1-to-1 ratio in the structure. So we did that. We just managed to lay out 2 dimensions using only these 2 structural units. And it works. So that means that structure looks very amorphous, right? But it's possible to classify it quite simply. I should say that just by looking at that structure, I might understand your confusion. The structure looks very dissimilar, right? But in fact, they are actually very similar, because if you remember, for the phase change memory applications, we need to switch very fast. A switch speed is switch time is between 10 and 100 nanoseconds for the phase change memory applications. And this material switches very well. So there should not be so big difference between these 2 structures. So essentially, the crystalline structure and amorphous should be just distorted enough to have a different transport properties, but they should be close enough to switch back and forth fast. And then we were like looking into the 3 dimensions here, and the answer is surprisingly simple. So to switch between amorphous structure and the crystalline structure, one would need to move only a single atom, only by about 2 angstrom. So this is this atom, germanium atom in the middle. You see the octahedron around the germanium atom, and now when you move it just enough to bound to become in this tetrahedral arrangement, then you'll get the tetrahedron here. And this movement of the atom, 2 angstrom movement, should be fast. And of course, it also triggers a little bit of reconstruction of the other two atoms around this, but essentially, in a nutshell, it's a single movement, it's a movement of single atom, I'm sorry. This is a very encouraging for us. Why? Because we see the perspectives that we can scale down our memory cells to a single atom. So this will be a single atom memory, ultimately. So, yeah, that's all I got to say today. And before I turn to draw my conclusion of the lecture, I'd like to go for acknowledgement. I'll do acknowledgement in order of appearance, if you allow me. So first thanks should go to these two gentlemen. So the old guy with stylish mustaches is my great-great-grandpa, Maksym. He could not write well. At that time, that was normal. But he was very convinced that education is the key. So he made everything possible that his kids were all educated. The small boy next to my great-great-grandpa is my grandpa. His name is also Maksym. He was my first physics teacher. He was my first math teacher. He was the source of inspiration and for me and for all my brothers and cousins. Thank you, Granda. So next thanks should go to my dad and mom. Thank you, Mom and Dad. I know you're watching up there in the virtual audience. I would like to thank you for the best childhood, full of creativity and freedom of choices. I would like to thank them to Olesya and my two kids, Mariana and Matvey, who are here in the audience. Thank you for all the love and emotions you give me. Yeah, the kids used to be small, so I could hug them all at once, including my wife. Now kids are much bigger, so I shall hug them one by one. So I'd like to thank to Vanessa and to all Institute for Electronics. You're great people and the best possible environment for the science. And yes, Vanessa keep promoting me first to senior assistant and then to assistant professorship. So thank you, Vanessa, for all the trust you give me. There are many people I would like to thank to all members of my big family, all my mentors, some of them are in the audience, all collaborators, colleagues of CMD group and MADE group, the former colleagues in different institutions, and also my friends. I wouldn't name them though, they are all here in small but golden letters. So now coming back to conclusion. So what did we learn about complexity today? Complexity is mesmerizing. Complexity is brain intense, and complexity can be fun. So there will always be some puzzle of nature which we scientists are going to tackle. But complexity shall not be the goal of research. In fact, complexity is a function of research. Complexity is a function of how the project is developed. When we take up on any question, we enjoy the complexity. And while we're working, complexity increases until we meet, so to say, Eureka point. You may call it an invention. And these are, believe me, these are the best moment in the life of scientists. So the Eureka point is over there, and once it's understood, everything becomes much, much simpler. So as one big said, everything should be made as simple as possible, but not simpler. Thank you so much.